This video is the first in a 4-part series about the basics of electricity and magnetism. The goal is to give you a general intuition for where each idea comes from, not to rigorously prove everything or go through every example. The first video here is about electricity, so electric fields, Gauss's law, voltage, that kind of thing. So let's get started. This is an atom. In the center are protons with positive charge and neutrons with neutral charge. On the outside are electrons with negative charge. Like charges repel each other, and opposite charges attract. And we want to measure how much they attract or repel each other. But there's a problem with that.
In reality, you don't just have a charge floating around like somewhere in space, right? Everything has atoms. So instead what you get is a situation like this, where one object has more positive charges than the other one, so it's kind of a positive region of space. And then on this side, you have more negatives and positives. So you have a negative region. And so now I have a positive region and a negative region. So those are going to want to attract each other. So what you can do is you can take two objects like glass and cloth. And if you rub them together, then the electrons are going to get removed from the glass onto the cloth. So it has more protons than electrons, which means it has a positive net charge. So if I take two charged objects, I can measure the force between them. And if you do that, this is what you get.
The force between two charged objects is proportional to the charge on each of those objects. So if I double the charge on one of the objects, the force between them doubles. If I double the charge on the other one, the force also doubles. If I triple it, the force triples. So Q1 here is the charge on object 1, and Q2 is the charge on object 2. It's also inversely proportional to the radius squared. So if I double the distance between the objects, the force gets cut by a factor of 4. If I make them 10 times further apart, the force is going to go down 100 times. And so now if I combine all of these, what I get is that the force is equal to some constant times each of the charges divided by the radius squared. And this is known as Coulomb's law. And one thing you might notice is that this looks very similar to gravity. In fact, if you look at the gravity equation, you're going to see that it's almost identical, except instead of charges, we're looking at the mass of each of the objects, so m1 and m2. And then also, the constant out front for gravity is a lot smaller. In fact, the electric force is about 100 quintillion times stronger than the gravitational force.
So that's how things would work if you had two charges attracting or repelling each other. What if you only have one charge?
So let's imagine we have a positive charge, and we pick some point out in space and we say, hey, if I were to put a charge here, what would happen to it? Well, we already know the magnitude of the force. It's kq1 q2 over r squared. And we know that they're either going to attract or they're going to repel, which means that the force is going to point from one to the other. So if we make a unit vector, that's a vector with length 1, pointing from the positive charge to our point, we'll call that r hat, we know that this is going to give us the direction that the force is going to go in. And if the charges are opposite, we'll end up getting a negative sign, so the force will point in the opposite direction. Which makes sense, right? Because negatives and positives should attract each other. If we set the charge at this point equal to positive 1, then one of our charges will end up dropping out of the equation. And what's left is the electric field. So the electric field basically tells us how much force we're going to get if we put a positive 1 charge at any of these points. So at this point, the electric field might look something like this, or we could draw the electric field everywhere. And so this is going to show us, hey, if I put a positive charge, it's going to flow away from the one in the center because the positive charges want to repel each other. And you can do the same thing for a negative charge, except now the arrows are going to point inward because our hypothetical +1 charge is going to want to attract the negative. Or you could put a negative and a positive together. And in that case, at every single point, you just calculate the electric field from the negative charge plus the electric field from the positive charge.
If you want to calculate the electric field from a continuous object, all you have to do is break it up into a bunch of tiny charges and then just add up the electric field for each of those charges.
So, for example, if I have a continuous line of charges, then I can break it up into a bunch of tiny pieces and calculate the electric field from each piece. The way you do that is just by doing kq over r squared like normal, except now our q is infinitely small. So we're going to use dq, a differential charge, instead. But what exactly is dq equal to? Well, if we know the total charge on the line, let's call it q, and the length of that line, then we can get the charge density is just the charge divided by the length. Now if you multiply that by the lengths cancel and you just get charge. So we can say that the differential charge is equal to the charge density times a very tiny length, dx. And now if we add up the tiny charges with an integral, we can calculate the electric field at some point. And if you want to do it for some other object, you just gotta find another way to break it into tiny charges like this. So if we want to solve this integral, we could pick a point that we want to solve for, call it P, then we can find the radius with the Pythagorean theorem, we can find the r hat vector, we can solve for all of this. And the only problem we're going to run into is that sometimes it's pretty hard to calculate this. I mean, would you want to solve for that? But luckily, there's a much easier way we can solve for the electric field. But to do that, we have to talk about flux. Let's say I have a vector field that represents the wind, and I want to catch the wind with a net. How can I create a way to measure how much wind is caught by the net? Well, we know that if the wind is blowing stronger, then it'll probably catch more. And also, if the net is bigger, it'll catch more too. And then lastly, if the net points perpendicular to the wind, we'll get more. So in order to describe this, we'll need to get the net's area vector, which is just a vector that's perpendicular to the net's area, so the circle right here. And then the length is equal to the area. So if the circle here, has an area of 5, then the vector is just going to have a length of 5. If either the wind is bigger, the net's area is bigger, or if they point more in the same direction, then we'll catch more wind. Which means that we can write our ability to catch wind as the dot product of the wind and the area vectors. And this is exactly what flux is. It's just how much a vector field flows through a given area. And if you have a more complicated surface, then you just need to break it up into tiny areas, dAs, and then add up the flux across the whole surface. So you get integral of w dot dA. Now the electric flux is just how much electric field flows through an area. So to calculate electric flux, we'll start with the charge and we'll surround it with a sphere like this. And to make things easier to see, we're going to draw it in 2 dimensions, but remember that we're really making a case for 3 dimensions. We've already seen that the electric field for a positive charge points outward because it repels that hypothetical +1 charge. And our goal is to find the electric flux on this sphere. So to do that, we're first going to restrict our view to the electric field on the surface of the sphere, so like this yellow region right here, and we can see the differential area vectors are going to point out away from the sphere because they have to be perpendicular to that surface. Writing out the flux equation, we get this, where the circle just means that we're adding up over a closed surface. Since both the electric field and the area vectors always point away from the charge in the same direction, then we can simplify this from the dot product to simply the scalar product, EDA. Now recall that the electric field is a function of radius, but in the case of a sphere, the radius is constant, which means that we can pull the E out of the integral like this. And now we're left with just the integral of differential area, which means that this can simplify to area, and the entire flux through the sphere ends up becoming EA. So now we can start plugging things in. For the electric field, we have kq over r squared. For the area of our sphere, it's 4 pi r squared. We can cancel out the r squareds here, and then we'll also usually rewrite these constants, 4 pi and k, as a new constant, 1 over epsilon naught. And this is Gauss's law. The electric flux is equal to the charge inside the sphere divided by epsilon naught. And the thing that makes this powerful is that it also works for any closed surface, usually called a Gaussian surface, not just a sphere. To see why, we can surround the sphere with a completely general surface. As long as it's closed, it doesn't matter what kind of surface it is. Now, we'll extend 2 line segments from the charge to each of the surfaces. We'll call the area enclosed by the sphere A1 and the area enclosed by the general surface A2. The radius to the sphere is called r, and the radius to the general surface is called some scaling factor n times r. Now, as we've seen before, we can rewrite the dot product in its cosine form. So the electric flux for the second area is equal to the electric field at the second area times the cosine of theta times some small area 2, all added up across the second surface. Now the angle theta is this one right here, and it points between the electric field and the area vector A2. Now the component of A2 that's perpendicular to the electric field looks like this blue circle, and in fact it's the same as A2 times the cosine of theta. To see why, let's look if theta is 0. In this case, the cosine will end up going away because it's 1, and we'll just get the electric field times the area, so it's the same as the perpendicular component. Now if the angle is a right angle, then the cosine will be 0, and there will also be 0 perpendicular component. So we can rewrite the flux integral as the accumulation of the electric field at surface 2, E2, times some differential perpendicular area. Now remember that the electric field goes like kq over r squared. So if our radius is now n times r, we'll introduce a factor of 1 over n squared into the equation. Now another thing we can do is we can pull out the projection of these two line segments into areas, and then we'll get two triangles that overlap each other like this. We'll call the length of the middle segment d, the diameter of area 1, and since the triangles overlap like this, they're similar triangles, which means that the ratios of the side lengths have to be the same, and so the length of the top segment has to be n times d, and this is the diameter of the perpendicular area. So now, if you recall that the area of a circle is pi r squared, which is the same as pi times half the diameter squared, if the diameter increases by a factor of n, then the area has to increase by a factor of n squared, which means that our dA perpendicular is the same as dA through the first sphere times n squared. Now we can cancel out the n squareds in the integral, and we have the exact same flux integral as the sphere, which means that the electric flux through A2 must be equal to the electric flux through A1. And this will hold true for every single dA as we integrate across our general surface. Now let's take a minute to think about what would happen if we had another charge inside the surface. So we could surround it with a sphere, just like we did before, and we can make the exact same flux argument. And since the fluxes are going to add because the electric field adds, then we'd find that the flux is now just the sum of the flux from the charge. So we could say that the flux must equal the total charge enclosed by the surface divided by epsilon naught. And just for completeness, if we have a charge that's outside the surface, say over here, then it'll have a flux that goes both into and out of the surface. So if we use the same arguments, the amount of flux going into the surface has to equal the amount of flux going out of the surface, and so they're going to cancel with each other, leaving us with zero net flux for charges that are outside the surface. And so now we have Gauss's law. The electric flux through some closed surface around some charges is equal to the charge enclosed by the surface divided by some constant. And now we can calculate the electric field much more easily. So let's look at an example. Let's say I have some large sheet of charge. Now the electric field on the sheet of charge is going to point away from both the top and the bottom, like this. So if we want to find the electric field some distance away from the sheet, we'll need to create a Gaussian surface. So we're going to go ahead and bring in this cylinder. And then just to simplify things, we're going to go ahead and make each of these one vector, and we'll make them go through the cylinder like this. As a reminder, here's Gauss's law. Now we're going to go ahead and start solving the left side. Since we're at a constant distance from the charge along the cylinder, and the electric field is always perpendicular to the surface of the cylinder, then this integral simplifies to E times A, where A is the area of both the top and the bottom circle. So we get 2 pi r squared with the E out front. Now for the right hand side, we'll have to make some assumptions. Specifically, we'll go ahead and say that the whole sheet has a charge Q, and the whole sheet has an area A. The charge density, sigma, is the charge per unit area, so Q over A. And if we want to get the charge, we just have to multiply by the area. So the charge of the region enclosed is sigma times pi r squared, since pi r squared is the area of the circle that encloses the charge. And don't forget to divide by epsilon naught. Now we can set these two equal to each other, cancel out the pi r squared, and divide by 2. We'll get that the electric field is equal to sigma over 2 epsilon naught. And that's it. It's a much simpler calculation.
And now we have to talk about voltage, which is kind of like potential energy, but for charges.
If I have some object, like a square, and I apply a force to it, and it also moves some distance from that force, then I can find the work as the force times the distance times the cosine of the angle between them. So, if the force and the distance are in the same direction, the work is just the force times distance. If the force is perpendicular to the displacement, then there's no work. And if the force is in the opposite direction of the displacement, then there's negative force times distance work. So the work really measures how much the force and the displacement are aligned with each other.
So if you think about the potential energy of this ball, right now I'm holding it up, which means it has the potential to fall down, right? And if I pull it higher up, it's going to have more potential energy because it can fall further down. So mathematically, what we kind of say is you have the force of gravity pointing downward. So when I move it against the force of gravity, so the displacement is upward, but the force is downward, I've created potential energy because now it has the ability to go backwards following the flow of gravity.
So this means that when you do negative work, you get potential energy. We're also going to go ahead and rewrite the right side as a dot product just because it's a little bit more compact. Now, if the force changes as we move along the path, then you can add up the work done by each little point in the path. So you can add up the work from delta S1, delta S2, delta S3, and you can imagine that if we add up all of these and then we make the distances as small as possible, then we're going to get the best approximation that we can. So the potential energy ends up being this integral. And if we want to solve for the electric potential energy, we can go ahead and put in the electric force equation we have, and then our change in distance, we're just going to make it go in the r hat, the radius direction. So if we bring it in some small change in radius, dr, in the r hat direction, we'll start with the two charges infinitely far away from each other, because if they're infinitely far away, they're not going to really exert any forces, so they're not really going to have any potential energy. And we'll bring them in to some radius r prime. So if we go ahead and we solve this equation, what we get is that the potential energy between two charges is going to be k, q1, q2, over the radius between them. And now we're ready to talk about voltage, because voltage is just the potential energy per unit charge at some location. So just like the electric field was asking, hey, what force would I get if I put a +1 charge here? The voltage is saying, hey, what if I put a +1 charge here? What's the potential energy going to be like in that situation? Now, if you look at the equation on the top, you can see that we can also solve for voltage by dividing both sides by the charge. On the left-hand side, we'll get potential energy divided by charge, which is just our voltage. And on the right-hand side, we'll get a 1 over q. But if you notice, there's also the force here. If we have the force per unit charge, what we end up getting is the electric field. So now if we simplify this equation, we can see that the voltage is just the negative of the accumulation of the electric field across some distance. So that means that if we take some charge in the electric field and we move it against the electric field, we create voltage or electric potential, because now the charge has the ability to flow along the field back in the direction it came from. If we want the absolute voltage, we'll have to do the same thing where we go from infinity to our radius r prime. But if we just want the change in voltage between two locations, then we could just go from location A to location B. And there's another thing to notice here. So remember how earlier we said that if they're perpendicular, then there's going to be no work. Well, this also means that if the electric field and our change in distance are perpendicular, then there's going to be no change in voltage. So if we go back to our original electric field here, and we draw lines perpendicular to the electric field, all of those lines are going to be at the same voltage, which is why we call them equipotential lines, same voltage. So we can go ahead and label these. Maybe the left side is -1 volt and the right side is +1 volt. You know what this looks a lot like? A contour plot. Except instead of elevation, we have voltage. But what if our voltage was our elevation? Well, then we would have something like this, kind of like 3D map of the voltage, where you can see that positive charges kind of push up and create hills, and the negative charges stretch downward and create valleys. And since the electric field points perpendicular to the contours, because the contours are perpendicular to the electric field, right? They're kind of perpendicular to each other. Then the positive charge is always going to be following the path of steepest descent. So what we can imagine is if we bring in a positive charge up at the top of the hill here, then it's going to follow the path of rolling downward into the valley, because that's where the voltage is the lowest, so it's decreasing its potential energy. Now, if we had a negative charge and we put it at the bottom of this valley here, it's actually going to roll upwards, because you think all of the signs are flipped and we have a negative charge. So another thing you can notice here is that these charges aren't actually going to care how high or how low the hill is, right? When they're rolling down the hill, the only thing that matters is that lower down on the hill is lower than where they are.
So if you have a 9 volt battery, what it really means is that one end has 9 volts of more potential energy than the other end. Not that it's at exactly 9 volts, because you can kind of pick wherever you want to be 9 volts. But that also means that if you get two and you connect them together, then this side is 9 volts higher than this end. But also this end, the end of this bottom battery, is 9 volts higher than this end, which means that across these two, you have 18 volts. Now, if you get a piece of pencil lead and you connect it across them, what you should notice is that it starts catching on fire a little bit. You see that? And the reason is because it has a low resistance.
But before we talk about that, let's take a minute to review what we've learned so far. So we've seen four main quantities. The first is force, which is a push or pull on an object. And between two charges, it's some constant times each charge divided by the distance between them squared. Electric field is the force that would occur at some location if you were to put a +1 charge there. One of the charges ends up dropping out of the equation, so we get some constant times q over the distance squared. Voltage is the electric parallel to potential energy. Specifically, it's the potential energy if you were to put a +1 charge at some location. And potential energy is the ability of some object to do work. So when you push something against a force field, you create potential energy because now it can move through the force field. We can get between electric field and force by adding or removing a charge. So we end up multiplying or dividing by Q. We can get between voltage and potential energy by adding or removing a charge. So again, multiplying or dividing by Q. You can go between electric field and voltage by adding up the negative accumulation of the electric field or finding the slope of the voltage. And then we get between force and potential energy by, again, adding up the accumulation or taking the slope. In the next video, we're going to see what happens when we connect the ends of a voltage source, creating a circuit. If you want to bang out all the other 3 chapters right now, they're all out in one big video. Just check the description or somewhere. I'll have it up.